Yeah, sorry. Just coming into class and got stopped by one of the chemistry professors there, and so we're talking schedule and no, not chemistry. That would have been much more exciting if we were talking science than schedules and that kind of thing, and organizing class and sharing classroom space and equipment and all that good stuff. All right, well, let's go back to where we left off. We were well into chapter 10, and so that's where I want to pick up. I do got a lot of stuff to throw back to you here, so I guess I'll just get that started. That can go around for the next 2 hours there. There's a bunch of homework chapters. I do want to throw this back at you. Here is a great opportunity to learn more about transferring to UCSB here, and so this is a little much for this class. Maybe I'll cut it in half and send it around, and I'll pick up the extras later. But I've been trying to give this to all my classes, in part that I think it's a very good idea and beneficial. If you haven't got a chance to meet Tacey and hear her little talk and ask questions, you guys are in a good opportunity to do that in that position, in the sense that probably most of you are in the position where you're not applying to the UC system now, this November, but definitely next November. And so that's what you should be gearing towards. And so hearing her speak would be good, even if it's not UCSB is your goal. And I should also point out is don't forget today is transfer day. So when class is done, if you wanted to swing by all those tables, they've got a million four-year institutions, and maybe not quite a million, but a lot out there, and can start talking to them and start going through the whole process of the application, because you are getting close to that. Maybe it's a year away, maybe even 2 years away, but can't learn it too early. All right, so where were we? Well, as I was trying to say here, we get into this chapter on rotation, okay? And it's a long chapter. It's a long chapter because everything we've done for our linear motion is repeated here. So, if you remember, I had a little chart over here. So let me kind of fill it in again. But what we had is we had a little chart here for dealing with rotational and dealing with linear, or a transverse motion, not necessarily meaning a straight line, but the distance divided by time type thing here. And so what we had is we said position, which was measured in meters, would be the same as the angle theta measured in radians. And then we said, well, back in chapter 2, after we talked about position, we talked about the rate at which position was changing, and we called that velocity, and so we had the units of meters per second, and we did the same thing here last Monday, and we said then we would have an angular velocity, where the angular velocity would be how the angle changes with time, just like the linear velocity was how the position changed with time. And then finally, this is about where we left off. We said there was then an acceleration, which was measured in meters per second squared. So we would have the equivalent for a rotation. So we would have a rotation or an angular acceleration, and that would be measured then in radians per second squared, and it would be the rate at which the angular speed is changing, just like the linear acceleration was the rate at which its linear velocity was changing. Okay? And so I think that's where we stopped. We did kind of put one more step in here. I'll draw that picture on the board. But we got into that discussion about a rigid object, and regardless of the shape of the object. Oh, and I just see it here that as you're passing around those other papers, if anybody wants to dig through this again, looks like you guys did a well job of digging through them last time. There's only a few more papers there. I'm kind of suspecting that those papers might be earlier ones from people who never picked them up back at the beginning of the semester, and they're not here anymore here. So we'll see where that is. But what we had was this, is we said, look, here's a piece of plywood, and if I take a piece of plywood and I cut it out with, say, a jigsaw, and then I drive a nail into it and put it on this wooden fence here, I could look at some point P, and what we were labeling it is something like this. We said, okay, the distance from the rotational axis to the point we'll call R, the angle from the x-axis we'll call theta, and so as it spins around, the angle will change, the rate at which its angle changes is its angular speed, and the rate at which its angular speed is changing is its angular acceleration. And then we went on to say, well, we could also think about its path it will take. And one thing I wanted to emphasize, and I'll say it again, that even though the object is not round, when it spins, the point P will make a perfect circle. Because this whole idea of a rigid object means that it doesn't change its shape. So the distance away continues. So with that said, then we took one more step here. And we said, if you measure the arc length as theta times r, and so I'll pause there. Theta would have to be in what units? Radians. Okay, so this was the part we said this was where the advantage would be of measuring in radians. If you took the time derivative of both sides, what you would get is this ds dt, and r, not changing for a rigid object, can be pulled out of the derivative, and then this becomes r omega, and over here then becomes the v, or what your author puts as v sub t, for that transverse or the tangential speed of it. And that's where we left off. We were spinning this and saying, all right, which one, if any, has a greater speed? And you respond by saying, yeah, which speed? A linear speed or a rotational speed? So they have the same rotational speed, but the one with the bigger radius then has the bigger linear speed, the bigger distance here. So put over here also, or maybe not put into this chart, is this connection here that the tangential speed is related to the angular speed, and as you'll see, that will become very useful as we kind of look at it in terms of how much angle is it rotating versus how much distance does it travel. And of course distance then would be a circular distance as it goes around. And so this is section 2 of your book, where your author says, what is the relationship between the rotational stuff and the translational stuff? And that's kind of the first equation he puts. But he goes on further and said, well, wait a minute. What if you take the derivative with respect to time again? And if you do that, you will get, on this side of the equation, the rate at which its transverse speed is changing. And again, treating r still as a constant for a rigid object, we would get a d omega dt on that side. And again, if you stop and kind of read this a little bit, isn't this an r, and this is what? Okay, good. Alpha, that's its angular acceleration. What's this over here? Yeah, that would be the acceleration. Now again, the tangential acceleration. But that's worth putting over here too, that the tangential acceleration is related to the angular acceleration. So again, there's another connection between the translational motion of the object, or the linear motion, if you will, and the rotation of it. And so as I look at this point P, and if this was spinning faster and faster and faster, what I could be looking at is its angular speed going faster and faster and faster, or I could be looking at its tangential speed going faster and faster and faster. In fact, I'm still not done here, because something else we learned, I guess this gets back to chapter 4 and also chapter 6, is that when you had something going around in a circle, wasn't there a centripetal, or what we called a radial acceleration? I mean, even if its speed isn't changing. And so you might recall in the discussions we had, something like this, that if you had an object traveling, say, in this way, and you applied a force or an acceleration at some direction, you know, different than the direction of travel, you could break this apart, and you can have this part of the force or this part of the acceleration that is making it go faster, and this part of the acceleration is the part that's making it turn. That's the part of the acceleration we call the radial acceleration. That was the v squared over r. You guys remember that? Okay, so as we're looking at this little point P going around, it is not just going faster, but it is also turning. So a second piece to this puzzle is not just this one, but also the fact that it would have radial acceleration. Or simply put, if this thing was just spinning at a constant angular speed, then these two, its angular speed and its tangential speed, would still be 0, but wouldn't it still have a radial acceleration? Not going faster, but still turning. Yes, that's still an acceleration. Okay, so what we learned back in chapter 4 was that it was equal to v squared over r. Using then this step here into here would change it into, well, I guess an r squared here, an omega squared there, one of the r's cancels off, and we get an r omega squared. So writing it in terms of angular quantities, we would get that. And then finally, putting the two accelerations together, in fact, you even had a test question like this on the first test. I forget, I think it was a train going around a turn or a car around a turn, but it was going both faster, or was it slower? Anybody remember? Slow, it was slowing down, but you had a car that was slowing and turning. And the whole idea is, then how would you get the total acceleration? Well, I guess we would have the tangential part and the radial part. And kind of showing it in this picture, we would see then the Pythagorean theorem. There would be the two pieces. Yeah?
Isn't that omega?
Oh, did I? Yes, thank you. I dropped off the squared. Now, good. There we go. Okay. Well, and so the final step here is a total squared is then this tangential piece and the radial piece. And that's what I was really hoping to get last Monday. Didn't quite get that far there. But that's the beginning part of this chapter. Going through the kinematics of just what is the connection between position, velocity, and acceleration. And I really wish we had more time, but as I said, this is a long chapter. The reason it's long, and the reason why hopefully you will find it easy, is you're supposed to make the connection. Everything that you did for the linear motion, which was quite a few weeks ago, repeat now again for the rotational motion. Let's see if this helps. When we were back here in chapter 2, I put this little diagram on the board. I said, if you had its position, you had its velocity or its acceleration, could you go from one to the other? And the answer was, well, yeah, they're mathematically connected. That is, if the derivative of position with respect to time gives you velocity, or to undo the derivative, if you integrate velocity, you get back to position. And so that was our our little diagram. And then also here, if you knew velocity, could you get to acceleration? Yes. Or if you knew acceleration, could you get back to velocity? Yes. Again, they're related with each other, derivatives and anti-derivatives. So I would say the same thing. If you know theta, could you get omega? Could you get alpha? How are these two related? Well, hopefully you're seeing exactly the same pattern, that the rate of change of theta with respect to time gives you the angular speed omega, or the integration of omega with respect to time gives you theta. So if you know one, you can get to the other. Likewise here, the derivative of the angular speed gives you angular acceleration, or the integral of the angular acceleration gives you the angular speed. And so exactly the same chart. And you're going to see this throughout this whole lecture and this whole chapter. So we won't have time to go back and repeat everything we did, but the whole point of me doing this and making this chart here is hopefully you will see the connection, because the quicker you see the connection between them, and if you got those analogies, you'll find this chapter is, oh yeah, well, that's how you do it. I would have done a free body diagram to solve this if it was linear motion, so I'll do a free body diagram for the rotations, and I'll look at the rotations. Or I would have done an integral, so I'll do an integral and just make a connection back and forth. Now the reason I say that is because if you remember in chapter 2, we started with this general picture, and then we said, let's look at a special case. What if acceleration is a constant? Do you remember what we did then? We said, okay, look, let's start here. Let's take acceleration as a constant and do an integral. Wouldn't that give us an equation for velocity? And does anybody remember the equation we got for velocity? Well, wasn't this it? It was initial velocity plus acceleration times time. All right. Now, in the interest of time, what if I said if alpha is a constant? What if I have an object that's rotating with a constant acceleration? Could I get an equation for omega, for its angular speed? Yeah, any guesses? Yeah, so initial angular speed plus alpha t, right? Angular acceleration multiplied by time. So back in chapter 2, we called this kinematic equation number 1, so we'll do the same thing. We'll call this rotational kinematic equation number 1. But remember, it's limited to what? Yeah, constant acceleration. So again, going back to that first test, you might recall that I deliberately gave you one problem with constant acceleration and another problem without constant acceleration to see what you would do. And most of you saw it, that you did an integral when it wasn't a constant acceleration. You didn't want to use that. Of course, that came from the integral. Well, again, without taking too much time, I will say that didn't we do this and get 4 different equations? I mean, didn't we take the next step and we integrated this, which would be here? Now that we have velocity, let's integrate that equation to get position. And we called it equation number 2. Again, it would only be useful for constant acceleration. You probably remember then it was initial position plus initial velocity times time plus 1/2 acceleration time squared, right? So that's what we came up with when we did the integral. So again, not doing the integral, what would that look like down here? Yeah, final position theta equals, yeah, initial position plus, yeah, initial speed multiplied by time plus, yeah, 1/2 alpha t squared. So you guys see it, and once you start seeing that analogy, things fall into place, as well as how do you solve the problem. Not only the equation's the same, but the thinking process of how you would solve it is the same. And that's what I'm trying to get across here. And that's what hopefully you'll see as you sit down and start to do these homework problems. And you said, well, it's rotating now instead of translating. But if it was a translation, I would have done it this way, so I will continue to do it that same way. Well, we had 4 equations. I don't know if it's worth putting the 4 in the terms of the linear motion, but I will put them here. Our next equation was number 3. It was basically solving this one for time and putting it into there. Maybe I will. We got final velocity squared is equal to initial velocity squared plus 2 times acceleration times the change in position. So the same thing would turn out to be here. You would have final speed squared is equal to initial speed squared plus 2 times the acceleration times the change in position, except our acceleration is now alpha and our position is now theta. And our last equation was this, that the distance traveled was equal to the initial and final velocity cut in half, or average velocity multiplied by time. So the same thing would happen down here, that our 4th kinematic equation would be initial speed and final speed cut in half multiplied by time. That would equal the change in position. And so there are our standard 4 kinematic equations that we used. And as you recall from chapter 2, you know, I kind of said, look, you really need to know this chart. This is the connection. You could always get this by integrating, but we use it a lot. Maybe you don't want, maybe you want to commit it to memory. And I said I like to commit the 1st and 2nd. The 3rd and the 4th, those are really derived from the substitution. This one we solved for time, put it into here, we got that one. This one we solved for acceleration, put it into that one, and we got this one. So I'm not sure 3 and 4 are worth memorizing, although we have found that they're convenient along the way. And so some of you did memorize all 4, some of you just the first 2. Hopefully nobody went beyond this. As I said, if you started memorizing all those other equations we did in chapter 2, that's just going to set you up to, you know, forget how do I do it? How do I come up with it? And that misses the whole point, you know, that physics is about knowing how to apply. Okay, you've heard it enough. Okay, but that's the idea here, is that just that few fundamental ideas explain that universe of phenomenon. And so again, this just repeats everything we did here in chapter 2. So like I said, there's really a lot of problems already we could do, because that's the equivalent of chapters 1, 2, and 3 all wrapped in together. And even more than that, because now not only do we have the analogy of chapters 1, 2, and 3, but then we have a connection to go back and forth. So we've got all this stuff plus the 2 different types of motion. So there's a lot of information there, and your author just throws it in 2 sections and says, hey, let's move on and talk about other things. So I am going to do that too, and hopefully then you'll see those other things. Because if you remember, after doing those chapters, we did other things. We did Newton's laws of motion, but after that we got into energy, and so that's where your author skips next. And so that's where I'm going to go here and say, let's look at this spinning object in terms of energy for a moment. Don't get me wrong, we will do the analogy of Newton's 3 laws of motion, but not yet. Your author skips over here and it says, well, look, if this thing is spinning, does it have a kinetic energy? Is there equivalent to an energy because things are moving? And probably doesn't surprise you that, well, yeah, I mean, it's moving in a circle now, and all the points are moving in a circle, but nonetheless, it still has energy associated with it. And so, if we go to write this out, you might say something along these lines, that if I were to look at the total kinetic energy of this spinning object, maybe I would start off by saying, let's look at a little piece right here. And why separate it into little pieces? Well, let me ask you this. And maybe I should change colors so you can see it a little bit better. But if I take two different points on here, two different small pieces of mass, and I think about these now spinning around, and I were to ask this question, do they have the same speed? Your answer would be, which speed? Linear speed or rotational speed? Okay, so do they have the same rotational speed? Yes. Oh yeah, okay. So something nice about that. Do they have the same linear speed? No, they don't. So if they had the same little mass, would they have the same amount of kinetic energy? No, right? And so you might say this, that looking at it in terms of a translational kinetic energy, it would be the sum of MIVI squared, where I equals 1, 2, and I'll just put an n up here, by saying, as I take this object and I break it into thousands and thousands and thousands of little pieces, each little piece, and let's just say each little piece has the same mass m, but each little piece doesn't have the same velocity. And that's probably not a good way then to write out its kinetic energy, because each piece has a different speed, linear speed. But don't they have the same rotational speed? So let's take advantage of that. Let's come back to this statement here and put that into this equation. And what will happen is I will get something that looks like this. Here's an mi, and again I equals 1 to n. Okay. But in place of their velocity, I'm going to put r omega, and so I'll put a little squared. But I do want you to notice something. I put a little subscript I for the r, but I didn't put one for the omega. Why not? Right, all these little chunks all have the same angular speed, right? The same omega. So there's no point in me putting a little sub I there. But there is a very important point of putting a sub I with the r. Do they all have the same radius? No. And so if I were to add all these together, I would see that I'm going to get some number, and each one is at a different radius, but each one has the same omega to it. Because watch this now. If I've got a bunch of these to add together, I guess the first thing I would notice is, doesn't everyone have a half in it? So I'm going to pull the half out in front of this big long summation, right? Half, 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 half. So won't have to worry about that part. Now each one will have a different position. So I'll need to keep position together there with its mass. But doesn't each one then have the same angular speed? Now this is the part that I'm hoping you're beginning to see why we did this analogy. Does this look kind of like kinetic energy? I mean, if I were to put on the board under this chart of linear motion kinetic energy, didn't we have it equal to 1/2 mv squared? Where m was the inertia measured in kilograms, right? Do you see anything here that might be useful? Do you see how this kind of looks like a 1/2 something speed squared? And so this little something is like the inertia. Now it's not just inertia. It does have a ER. It does have a position with it. And so it is a little more complicated than just inertia. But it is adding up the masses, and then it has the position of that. And hence the name moment of inertia, or maybe I should say why the name. It's more of a math term. Do you know what's meant by a first moment, a second moment, third moment? Yeah, well, in your math class, if you have a function and you multiply by position, let's say we integrate that, that's called its first moment. And then if we do this, and we take its position and we square it, that's called its second moment. And you can go on down, and it's third moment and fourth moment. And so isn't that kind of what we're doing here? Don't we have the sum of the masses? Don't we have inertia? But it's inertia multiplied by position, position squared. And so this is kind of a second moment, which I guess actually it's plural, moments of inertia for just that reason. And so it's our moments of inertia. But I suppose I shouldn't worry too much about the name. In fact, maybe I should take you back to Physics 102. What did we call it in Physics 102? Does this ring any bells? I think this is one of the harder things we did in 102. We just called it its rotational inertia. We just said, how difficult is it to get this thing to rotate? And I guess what I'm trying to say here is I'm trying to get you to see, and this is the first time you've seen it, but you will see it twice before today's over, that this little summation, that is, take the mass of the particle, multiply by its position squared, and add it up over the whole object, shows up a lot when we start having things rotating. And it shows up in the same idea of inertia. And so hence we call it moments of inertia, or sometimes a little simpler, it's rotational inertia. Although sometimes I got to be careful with that word, because I think by just saying the word inertia, students think only about its mass. And this is a definite difference then between the translational inertia. I mean, when we did translational inertia, we just said, hey, this is its resistance to change its state of motion. You have a lot of mass, it is hard to get it going fast, but also once it is going fast, it is hard to stop it. And that's what we meant by this word inertia. And we mean the same thing here by moment of inertia, that it has that same property. It's hard to get it to start rotating, but once it's rotating, it's hard to get it to stop rotating. Okay? And so it's really that same property, except it is more complicated because it is a summation of not just its mass, but it's also the position squared. And hence the name, moments of inertia. So the moments is telling you about its position squared, and then the inertia part of it is telling you that its position and its mass. Personally, I like that word rotational inertia. It gives me some feel for this. It is beginning to tell me why something is hard or not so hard to rotate. The standard symbol we like to use is I, and I guess I already did that right here when I put I here on the board. But if I put an I in here, and maybe I'll translate it then up to here, it's going to make it kind of nice to say, what is the kinetic energy of a rotating object? 1/2 I omega squared. And again, something that you hopefully won't have to commit too hard to memory, because you already know 1/2 mv squared, so hopefully it's obvious that the kinetic energy would be 1/2 I omega squared. Well, maybe the easiest way to illustrate I is with this contraption here. If I were to take these off, and you can see it is a platform that can rotate, would you expect the I to change as I put these on and take them off? If I take them off, would you expect the I, the moments of inertia, to increase or decrease? Decrease. Why? Okay, less mass. And hopefully that's the obvious one. And if I let this go, I want you to see how quickly it unwinds. But if I wind it back up, and I place these back on here, can you see that it is a little more sluggish, if you will? It doesn't unwind quite as quickly. Because, as you said, what I've done is I have increased the moments of inertia. And that one I think is pretty obvious, just because it's more mass. But here's another one. How else could I increase I? Good. You guys see it, that what I could do is not change the mass, but just change the position of the mass. And again, that's why we have that name, moments of inertia. It's not just inertia, it's not just mass, but it is the position of the mass squared. Watch what happens now. And wouldn't you say it's a lot more sluggish? The acceleration here is a lot less, and I should say rotational acceleration or an angular acceleration. Because, again, what I've done is I have changed the moment of inertia. What I have done is I have moved the weights to the outside. So, again, I just want to emphasize here that this moments of inertia plays the same role as inertia did for our linear motion. What is different, though, and significantly different, is it is not just inertia. It is not just how much mass you have, but it is where that mass is located. So you guys are seeing this in this little formula here. And that's something we did not do in Physics 102, at least too much on. You did a lab and kind of showed that it should be proportional to the radius squared. But in 102, we just talked about it conceptually. We just said, hey, what would change the moment of inertia? And you might remember some of the other little demonstrations that you saw in Physics 102, like that long rod that had the weights at the end that we were wiggling back and forth there. And so all of those were to illustrate how this moments of inertia is more than just mass. It's mass and distance. So with all that said, I'm hopefully have given you a good idea of what this is and how it is a little more complicated. What would be the units here? Okay, good. So the mass would be in kilograms and distance would be in meters. So you would get a kilogram meter squared. And so that is our units for this moment of inertia. Now, hopefully it makes sense. I mean, let's come back over to here. Let's say I was actually doing a calculation here. I mean, let me just give you some numbers. Let's say I is 10 kilogram meters squared. All right. Let's say omega is 5 radians per second squared. So if I were to give those to you and say, okay, what is the kinetic energy of this rotating object? Those numbers don't match this at all. In fact, the lab you're going to be doing real soon is going to ask you to measure the moment of inertia of this, and it's much less than that. But for the sake of conversation, let's say this is it, and this thing is spinning. Or maybe better still, since I can actually spin this one, is I'll put this one up here, and I'm spinning this one. And the question is, what is its kinetic energy? Well, let me put in my numbers. How does it work out? Well, I guess I would put in the 1/2. I'd put in the 10 kilogram meters squared. I would put in the 5 radians per second and square it. And it's not so much the numbers. I think you're seeing it's this little calculation is about the units here. But 5 squared is 25, and another 5 is 125. Okay, so there's my 125. My 125 what? Yeah, and if you look closely at this, it's kilogram meters squared, and then it's seconds squared, and I guess technically it's radians squared. But what's this part right here? Yeah, there's the joules. So it's 125 joules. What happened to the radian squared? Right, and what we said last time, it's not a real unit. It's something we throw in there to make it more clear, or we take it away if we don't want to mess with it, and it just makes things worse. So in this case, we don't want to mess with it. We take it out. So it is a kinetic energy. So remember this. When we're doing a problem with conservation of energy, and you did problems like this, like if I take my pen and I throw it, and I go, how high does it go? Didn't you use the initial kinetic energy to then become gravitational potential energy? So couldn't I do the same thing? Couldn't I start with a wheel that's rotating and have a little uphill ramp and place it on here? And how high up the ramp would it go before it stopped rolling? Wouldn't this rotational kinetic energy become gravitational potential energy? And there even might be some friction along the way, so there might be some heat. We might be compressing a spring. And so all those wonderful problems we just did on the test, we just need to add to it. And so we would have spring potential energy, gravitational potential energy, and then translational kinetic energy, and now rotational kinetic energy, and along with heat. And then we can do our conservation of energy. And by the way, you'll just see that continue, because as we go into next semester, we'll have things like electrical energy and chemical energy and solar energy, and the list goes on. And so our conservation of energy just has more to deal with. Yeah.
So if that was like a perfect frictionless system, would the MGH, like a little wave going down, be equal to the rotational kinetic energy of the...
Right. That's a very... Okay, either way you want to look at it, but it's a very good illustration of conservation of energy here. When this thing goes down, it loses gravitational potential energy. Where does it go? Well, it is going here to a rotation. Now, also don't forget there would still be some translational kinetic energy for that guy, right? And right before it hits the ground, it's got kinetic energy. So if I was solving a problem, as you suggested, I guess I would start off by saying 1/2, say little, oops. I would start off by saying mgy initial would be, say, the initial potential energy it has up here. Then as it goes down, and it gets near the ground, I would say it's moving, so it has a translational kinetic energy, and that whole thing is now spinning, so it has a rotational kinetic energy. That's a good example. And as you said, that's not counting maybe any heat or any friction along on the way. But your question went a little further and said, how do I look at that? If you look at this as one big object,
think of it as 4m, and m is the mass of each one.
Okay, or you could think of this as, I would say, 5 objects, where I've got 4 things on top and the disk rotating, right? So there's different ways I could write this last term, but that's coming up, so let me not jump too far down that road. But I can think of this, like I said, probably best is think of this one big object, and then what is the rotational inertia of the big object, which includes the disk and the 4 little weights or on top. Good. And great question, because again, unfortunately for this chapter, there's just not enough real time to really dive into say, hey, you know, what kind of problems could we give you? The author is saying, and I'm saying, hey, do you see the analogy? Do you see all the stuff you did with conservation of energy already in these last couple chapters? Could you just do it again? And obviously you saw it. You saw, okay, yeah, there it is. The potential energy gets converted into a rotational kinetic. And don't forget the translational kinetic of that one down there. And so that's exactly what we're going to be doing. And probably the best thing for me to do is just to keep going and throw all these at you and then do examples for you, and then of course let you go home and struggle on the homework and see if it makes sense to you and see if you can see the analogy as we go back and forth. Now, here's where I kind of want to, I don't know if pause is the right word. Open this a little bit, it's getting warm here. But your author goes on to talk about Newton's laws of motion. That's the other thing that we need to address. But I want to just focus a little more time on this rotational inertia. Because I've discovered in the past that both the idea and the calculation of rotational inertia has given students a hard time. So let's do this. Let's actually do a calculation. Let's start with some simple ones and build up here to something more complicated. Let's say I do this. Let's say that I've got two objects, and they're kind of small objects here, okay? And I'm purposely going to pick them as small ones for just a second. This happens to be 100 grams, all right? So I am going to take this 100 grams, and I'm going to place it 10 centimeters out. I've got another one that's 50 grams. And I am going to place it 5 centimeters out. Okay? Now, for this first one, let's just say the disc up here doesn't weigh anything. But I want to get this thing to rotate. I want to know its kinetic energy. Or, as we'll see when we get to Newton's laws of motion, there's other reasons I want to know this I, this moments of inertia. Could I calculate the moments of inertia of these two objects? Well, let's give it a try. I think this is the easy one. This is the one where it's like, okay, I've got two objects. They're sitting on this platform. Now the platform is massless. Obviously not a real case. We'll build up to that in just a second here. But the first thing I do is say, okay, let's find I. Well, I is the sum from I equaling 1 to n of this mi/ri squared. And I pick this one because what is the value of n in this case? How many objects do I have? Just 2, right? All right, so from 1 to 2, and I've got my masses of my two objects. I'm going to add it together. Now, wait a minute. This is a little different formula, but didn't we do the same idea for the center of mass last chapter? And didn't we find the center of mass? Remember that little sheet metal piece we had, the square, and we cut it out, and then we said we had to find the center of mass, and we treated that as 6 pieces. And then we did the Romeo and Juliet problem, so we had 3 pieces. We had Romeo and Juliet in the boat, right? And then we did the triangle. Remember how we found the center of mass of the triangle? How many pieces did we cut it there? Well, experimentally we hung it 3 times to find it. But didn't we mathematically calculate the center of mass too? By dividing the thing into an infinite number of pieces and adding together. And how did we add together an infinite number of pieces? What did we do? All right, we did that integral. Think anything's going to come out of that right now? Same game. Same song and dance. I'll start with the 2 though. All right, so let's start with the 2. In this case, I would say I've got my first object, and that was 100 grams, I said. So I'll put it in kilograms. So that's 0.1 kilograms. And I also said I have placed it 10 centimeters out, which I'll change to meters. And so that would be my first mass. 10 centimeters out, 100 grams. The second one was 50 grams. So I'll put that as 0.050 kilograms for its mass. And I had it 5 centimeters, which I'll write as a centimeter and square that. And so hopefully you'll see here in terms of units, it's a kilogram and a meter squared. And the number itself is going to be pretty small. It is 0.1 times 0.1 squared plus 0.05 times 0.05 squared. And 0.001 1125, the number comes out to be here. Okay? But there would be my moments of inertia. And then if this thing was spinning around, not too fast, otherwise it'll fall off there. But if it was spinning around with some angular speed, couldn't I calculate the kinetic energy from that? Okay, and now let me not take the time, because I think that's going to be the easy step. I mean, once you've gotten this moments of inertia, then just multiply by half, multiply by the angular speed squared, and you're good, right? Let's try a little harder problem. Let's do this. Let me take these two weights off here and go to a meter stick. We'll often refer to this as a rod. And basically what I mean by that is, does it have a thickness? Yeah, but not much. Does it have a width? Yeah, not much. Most of it's all about length. So let's do the same thing. Let me put the meter stick on here. And again, kind of that same question, that same pattern. Could I find the kinetic energy of this thing rotating? Sure. I would need to know its speed and its moment of inertia. So what is the moment of inertia of this thing? How do I do that one? All right, so let me put I of a rod. Would that be the sum of I equaling 1 to n of mi squared? And so what's n here? How many pieces do I have? Do you see here that every piece, if we divided this up into a bunch of pieces, is a slightly different r? Are you seeing this as a calculus problem now? Can you change this into an integral? Remember I said we've done this a few times and we're going to do it again here. And it looks like you guys are starting to get used to it. That's part of this whole semester, that if I kind of set this up now, next semester, you'll be able to do it on your own. Or you won't have to tell me, I won't have to tell you how to set up the integral or whatnot. Well, let's try it here. Let me draw a picture up here. So what I have is I have this rod here. I'll put a dotted line here for the axis. So this is the axis that it's going to be spinning around. But mentally for me, what I'll do is I'll kind of just divide this into pieces. There would be one piece and another 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 piece. And let me not draw all of them, then it gets too messy and you kind of miss the point here. But what I'm really saying is this. I am going to add these all together. What I'm going to do, and I'll just pick one right somewhere out here, some distance x from my rotational axis, and say it has some mass, mi. And so really what I am doing is this summation. As I heard someone say, how many pieces am I chopping it into? Yeah, an infinite number of pieces. What I'm doing is saying then that the I of the rod is a summation, if you will, from I going 1 to infinity, if you will, of an mi squared. And this is why you learned calculus before you came to this class. This was that difference between Physics 102 and here 121. And this is why I'm asking you to take these skills that you learned in 102 and the math skills you learned in Math 150 and put them together. And we can then solve this problem. This is a problem we couldn't have done in 102. What is the moment of inertia of this long rod? Now, for the sake of putting some numbers up here, let's say the rod has length L. Just so I can make it generic. I know that it's a meter stick, so hopefully you do know the length of a meter stick. That's one of those easy questions. Although it kind of reminds me of a story a few years ago. Final exam, I kid you not. Final exam, I had it was a problem, something to this effect that there was a meter stick out here, and it was on a little pivot right here, and the problem said let it go, let gravity pull it down. What's the angular speed when it gets here? And 2 students at the end of that final exam came up to me and said, you know, I think I did really well on the final. It was that one problem with the meter stick, and I didn't know how long it was. I could have finished it. Really? Yeah, I didn't know what to say. All I did was say, well, you know, when was the War of 1812? And I don't think they got it. They just walked out and said, oh, well, why is he asking me about history? This is a physics class. I don't get it. But they just missed that connection. Anyways, but yes, I know this is a meter stick, so I didn't want anyone to think I didn't know how long a meter stick was. But let's just, for the sake of conversation, call it L, and go through the pieces here and start adding these together. Because I think this is the hardest part of learning this. This is what I call applied mathematics. Yes, you went through your calculus, but when you were doing your calculus, you were told, do this integral, do this hard integral. You weren't saying, come up with the integral, and that's really what I'm asking here. I asked it last chapter, I asked it in chapter 7, I ask it now. I'll ask it one more time before next semester, and I start saying, do it yourself, you can figure it out, right? So what is my next step here is to mentally think of, what am I taking the limit of? I mean, when we take about a limit here, we're chopping things up. So what gets smaller? Okay, so it's the size of the mass, right? So is it the R? And I think this is the hard part. It is not the R, is it? What is the R in this equation? Right, it's how far it is. So as you chop this thing smaller and smaller and smaller, what's happening is the mass is becoming smaller and smaller. It's the M that is becoming smaller and smaller and smaller. It is not the R. Now, you might say it's the size of it too. Okay, and that's going to be the trick to this, just like last chapter. Because if you write it as you have it right now, it would look like this. The summation of an infinite pieces is an integral. And what you've done is said it's an integral of r squared dm. And so there's our first step, and a big step, and an important step. It's the way you'll see it with your author there. Your author will say, this is the integral form of how you get the moments of inertia. And I'm hoping now, and it looks like you guys are, getting to the point that you see that this big S here stands for summation. Right? It is the summation of a bunch of pieces. But again, I think that tricky part is right here. What are you making smaller and smaller as you are chopping it up into more and more pieces? And that's something you didn't do too much in your calculus class. You learned how to do the integrals, but not so much how to kind of set them up or to begin there. And so we saw this for the last couple of chapters, particularly last chapter. But of course, this is just like last chapter. We had a dm. A dm is not very helpful by itself. We do have to change it to a dx. And somebody said that, well, the x is getting smaller, the size. Yes, it is. But that's not in this equation yet. And so my next step then will be, like we did last time, is about density. What was the definition of density? Okay, mass per, and we could say volume if you want, and I will if you prefer, although since this is just kind of a one-dimensional picture, will it be okay if I just say mass per length for now? That be okay? All right? And so I'm going to say it is a little bit of mass in a little bit of length. And so this little mass right there, this dm in a little bit of length is the density. And that's the same way we did last chapter, is we changed the dm into a rho dx. Actually, I guess last chapter we changed it into a dA because we were doing a two-dimensional triangle, and so we said mass per area. Now I'm just doing a one-dimension. In a minute I'll do a two-dimension, but this will be my mass per length. So again, wanted to make sure we went through this one more time before the semester was over so that you'll be experts at it as you continue on in this sequence here. But notice again how I changed it first to an integral with a dm, and now I've changed it to an integral with a dx. So now I think you can begin to do it. Let me just put in a couple of things here that hopefully are the easy parts of it. I'll start with the r. What's the r in this? Yeah, I guess I'd call that the same as the x, where if I am talking about this equation, r meant that distance from the rotational axis to that little chunk of mass. And looking at this picture, that's what I have. The axis is here, and so measuring from the axis of rotation as my x and r become one and the same that way. So that's kind of nice. So I have an x squared. And the other thing I might ask is, what is my limits of integration? What am I adding up to and from? Yeah, negative L over 2 to a positive L over 2. I'm going to do the whole rod, right? I would be saying, okay, let's start with this little chunk over here and add it up. When I got to 0, that's half of it, and then I can do the other half.
Do you put it twice the integral of 0 to L?
Okay, fair enough. If you wanted to go 0 to L over 2 and then double it, that is what we call a symmetric integral, and that would work too. So, yeah, whichever way you prefer. Okay. But I think it looks better, I don't know, debatable, but I kind of like it from negative L over 2 to L over 2. It kind of shows that I'm adding up the whole rod, from one end of the rod to the other end of the rod. Now I think, like I said, this is the easy part. This is actually doing the integral. And so I'll pull density out in front. I'll do the integral, which gives me an x cubed over 3. I'll put in my limits of minus L over 2 to plus L over 2. I'll then put that into here. I'll leave the 3 and the density alone for a moment. This becomes an L over 2 cubed minus a negative L over 2 cubed, and I'll put that in brackets there. Okay, and so I've got my density over 3. This is L cubed over, and it looks like it's over 8, but this one's over 8 also, and the two negatives make a positive, so it's a 1/8 plus a 1/8, which makes a 1/4. So I'll put a 1/4 there. And then I'll make one more step here. It's this density step. We did the same thing last chapter. What was the last part we did with density? Well, we came back over here and said, well, density you can think of as a little bit of mass over a little bit of area. But if it's the same density all the way across, what's another way of looking at the density? The whole mass over the whole length, right? So why don't I do that? Why don't I call this the whole mass, capital M, over the whole length? And if I do that, then I get a 1/12 ml squared. And for any of you who are still heeding my warning about reading the chapter before you come to class on it, you will have looked here in chapter 10, and there's a big table, and it shows you a bunch of different shaped objects. And this is the first one they do. It says, what is it for a rod? And they give this 1/12 ml squared. Now, let me keep going. As I told you, I think one of the harder things in this chapter is this calculation of the moments of inertia. Both conceptually understanding it and using it in terms of our equations. Because I'm going to make a change here. Let me do this. Let me take this rod now and set it here. Which, of course, because of gravity is impossible. But let's say I had a little screw here. If I clamp that on there. And now I make it rotate. Oops. And I may be asking the question, what is its kinetic energy then? Well, again, wouldn't I need to know the moments of inertia of it? And would it be the same? It wouldn't be the same, or would? It wouldn't? Why not?
Because radius squared would make the further radius.
Okay, good. So you're seeing this whole concept that the moments of inertia is not just the mass of it. Now, did the mass of this change? No. But as you were saying, the position of the individual masses did in relationship to that axis. So is this going to have the same moment of inertia? No. So it's important that when we talk about the moments of inertia, and we come back to here and we say, what is the moment of inertia of a rod? We need to add to that about its center. Because I'm asking now this question. What is the moment of inertia of a rod about its end? And if I draw a picture up here, here would be the rod, here might be the rotational axis, here might be the little pieces that I divide into a bunch of chunks. But as you pointed out, I expect a different number here. And that's why we have to be careful back here and not just say, what is the moments of inertia of a rod? It is, what is the moments of inertia of a rod about its center? And this problem could be done in many different ways. We could say, what is the rotational inertia about its 30 centimeter mark? Would that be the same as its center or its end? No. So where you rotate it is very, very important. So let's try this calculation. Let's try it about its end here and see what we come up with. Well, maybe I'll start real quickly with going back all the way to the fundamentals here. Moment of inertia of any object is the sum of MIRI squared. But as we divide that into little tiny pieces, then what we are looking at is the sum of MIRI in the limit that the little chunks get smaller and smaller and smaller. And so this becomes the integral of R squared dm. And so that's this little step right there. This is how we would get the moments of inertia of what we might call a continuous object as the object spreads out here. All right, now I need to apply it to this case. Now, if I kind of set it up, the coordinate system, very similar like I did that, I said, well, let's look at that little chunk there. If that is x, again, measuring x from the rotational axis, then isn't r and x the same thing? Okay. So this becomes an integral of x squared. Going through the same logic that if I look at that little chunk, wouldn't its density still be mass per length? And so the dm would become a rho dx. And so nothing's different here yet. The big difference is, what are the limits? Yeah, so in this case, we go 0 to L. And as you said, what's different is it's going to have the mass at different positions. Hence, we end up with a different number here. And so, sure enough, we do. Let me do the integral here. There's the rho. This becomes an x cubed over 3, evaluated from 0 to L. So this becomes rho L cubed over 3. Then my last step is the same step we did here. The density thought of as the whole mass over the whole length then gives me a 1/3 ml squared. And maybe I don't know, should I put a box? I'm afraid if I put a box, you start memorizing it. But there's a lot of these figures we can do. There's a rod, there's a disc, there's a cylinder, there's a sphere, a hollow cylinder, a solid sphere. You know, a plane. You know, what is the rotational, a cube. Oh, there's a good one of the example problems. What is the rotational inertia of a cube? Okay, I think that's next chapter. Okay, so because that's a tough one to do. All right, so we'll build up to that one. But this whole idea here of that, what is the moment of inertia? So again, notice it has increased a little bit. Well, let me keep going with this. What about rotating about its 30 centimeter mark? Would it be that? Would it be that? How are we going to get it here? Okay. Could come back and change the limits of our integral, right? But let me show you something that the author shows you in the next section. He says, look, the difference between going from its center to something off-center is just changing its limits. Okay. There's a nice little mathematical trick that he's going to show you here that's going to make this real simple. So, again, those of you who've got a chance to read the chapter, you saw this. You'll notice that the author, when he lists the moments of inertia of these rotating objects, he only lists them about their center. Why? Well, I claim if you know it by on its center, a quick calculation called the parallel axis theorem can get it at some other point. So, even though I did 2 for you, the truth is I don't even need to do this second one. All I really needed to do was this first one about its center. Because once I know about its center, I can get it around any other point. Okay? Let's see. Here's what he does here. He says, all right, let's take an object. An object in general that is maybe more abstract in shape. I mean, these first 2 examples I did for you were rods. But he says, okay, let me just take an object that maybe looks like that. And let's just say we drive a nail into it right here. Now, I think you would probably agree that I'll do that, yeah. I think you'd probably agree here that that is not the center of mass of this, very likely. Now, it's hard to tell because I didn't say anything about the density, but let's just say it's uniform density across, okay? And if I was just guessing, purely guessing, I would probably put, it looks like center of mass here. It's probably about where the center of mass would come out to be. Now, here's why I say that. I'll put this on a red axis here. If I was calculating the moment of inertia around its center of mass, then wouldn't everything be measured from that red axis? But then if I switched axis and I put the nail at a different location, then I would want to know the rotational inertia about that point. And that's kind of what I did here first, right? I said, okay, what is the rotational inertia at its center? And now let's do it somewhere else, off of center. And of course, this changes your limits of integration. So in red, if I were to find the rotational inertia of this object, I would say, all right, what is the rotational inertia at its center of mass? And I guess I would do something like this. I would say, here's an integral. It would be an r squared dm, where r is something like this. It is maybe sticking out from here, and here's the little chunk of mass, mi. Oh, well, now that we're doing our calculus, let me call it dm. And I'd say, okay, there's that little chunk of mass. And I wouldn't do it for just that one chunk. I would have another chunk and another chunk and another chunk. But let me not put them in the picture, otherwise they'll get too crowded and you'll lose scope here. But if I were to add that up, isn't that how I would get the center of mass at that point? But let me do it in black here. What if I wanted to know the moment of inertia of that one? Well, this would be somewhere off of center of mass. Now, it would still be this same integral. But when I draw a vector out to that chunk of mass, it's not going to be r. Let me call it r prime. And I suppose I should even put a vector squared there. So this is a vector position squared position squared. But here's what your author does. He plays a nice little mathematical trick, and the results here are going to be great. He says, look, let's add another dimension in here. I'll draw it in blue. Let's say that the two axes are a distance d apart. And I'm hoping from that you can see, oh, and I guess I didn't finish here in my dm. This would be a dm. But I'm hoping that you will see that this r prime and this r in this diagram are related. That is d plus r is r prime. And I guess vector and vector. Because then he comes along and says, watch what happens here. And I'll just leave it in black here. But he says if you set this up and you take this r prime and you write it as d plus r and you square that dm, what do you get? Well, when you square, don't you get 3 terms? So this binomial squared. First one would be d squared. Last one here would be r squared. Oh, what about the one in between? Okay, it'd be a 2. It'd be a d. It'd be an r. And I guess technically it would be a dot product between them like this. Okay. But here's why I've done this, and this is why your author does it. Surprisingly, these 3 integrals are easy to do. Do you see them? And I would say you got to read this more than actually do them. Okay, we're back to that idea. What do they mean? For example, I'll start with this first one. The integral of d squared dm. What would that come out to be? Well, think about what you're doing here. This is saying add up the dm's. So you're adding up that dm and that dm and that dm and that dm. Does d change as you add up the dm? No, what is d here in this? Yeah, d is a constant number between comparing that axis and that axis. And so as you add up all your m's, you're not changing d. So I can pull this out here. And so I get a d squared. And what is the integral of dm? That's just the sum of all the little masses. If you add up the sum of all the little masses, what are you going to get? The big M, right? You're going to get the mass of the whole object. So that first integral is hopefully easy to see here. It is just a d squared and a capital M. The next integral. Ooh, I don't know if this one's so easy. to see. It's very easy to do once you see it. Maybe I'll write it this way. I can pull the 2 out in front. I can even pull the d out in front, and I'd have an integral of r dm. Right? Integral of r dm. Ever see that before? Let's see. What was the position of the center of mass? Wasn't it 1 over the total times the integral of r dm? And we just saw that in chapter 9. We get finished up. So, isn't this integral really the center of mass times the total mass? So I claim that this is 2d times the position of the center of mass times the total mass of the object. Wasn't that pretty easy? And I'm not even done. It gets even easier. What is the position of the center of mass? As measured from R, the red axis. 0. You put the axis right there. So I would say that number right there is 0. So what does this whole integral come out to be? 0. Ah, it's one of the easiest integrals you've ever done, huh? It's 0. It's the center of mass. Yeah. And then finally this last one. What is this last one? Isn't that the one I got started with? Isn't this the one in red? This one? The moment of inertia? As measured from the center of mass? And so this is the moment of inertia at its center of mass. Here's the conclusion then. The conclusion after all of this is to say that how do I get the moment of inertia of something away from its center of mass? Answer? Take the moment of inertia of its center of mass, this one, and add to it the mass of the object times distance squared. And so that's what I was saying a few moments ago. We really did not need to do this a second time. We did it right here at its center. And I claim from that you can find it almost anywhere else. You just got to move it a distance d. I mean, let's see if it works here. What did we get for the rod at its center of mass? Didn't we get a 1/12 ml squared? So if we start with that information, this is the moment of inertia of its center of mass, and then I move it over half the length of the rod, what is the new moment of inertia? So this would be plus m, and how far am I moving it? L over 2. Half the length of the rod. And I claim then that should have given me the same thing as this. So without having to do the integral for all the different positions and all the different shapes and adding it all together, what I really just need to know is what is at its center, and then I can find it someplace off of center. Let's see what it comes out to be. This is 1/12 ml squared. This comes out to be 1/4 ml squared. Common denominator is 12. 1 plus 3 ml squared. That's 4 over 12 ml squared. That's 1/3 ml squared. What did I get over here? Amazing. Right? 1/3 ml squared. So again, those of you who've kind of looked through it, or those who are going to look through it this weekend, you'll see this big table. This big table showing you the moment of inertia of different objects. I've just done the rod so far, but the reason the rod is there is because now I can get this anywhere. Shall we try a different shape then? Now we know how to do a rod. and we know its center, and if we know its center we can find it anywhere else, let's change. How about a cylinder? What if this was out here? Or maybe that's kind of a narrow cylinder. Does it still look like a cylinder? I know it's got little cutouts in it, but there's my cylinder. Could I find the rotational inertia of a cylinder? Ooh. How? Well, maybe I should start something a little bit easier. How about a hoop? Could I get the rotational inertia of a hoop? And that's one of the easiest ones we could do. Let's do a hoop. But again, I have to make that statement. A hoop about what axis? Yeah, is it the same if it's not at center? No, but I'll tell you this. If I found the rotational inertia of this hoop about its center, and then I moved it to here, and so now it's rotating around its rim, could you find it? How would you do it? There it is, the parallel axis theorem. If I know this about its center, aren't I just taking its mass and multiplying by its distance, which in this case would be its radius. We're going from its center to its rim. I could even do this. What about something that had a rod and a hoop? How about a rod, a hoop, and a cylinder? Could I find the rotational inertia of that configuration? What would I do? Good, and I'm claiming all you really need to know here is the rotational inertia of the rod, the hoop, and the cylinder about its center. Because if you know around its center, we can then have the rod by its center, okay. But then, if I knew the disk at its center, I could then just apply the parallel axis theorem and find out what is the cylinder moved a distance d. And then the hoop, the same thing. If I knew the hoop at its center, then I can just move it over there. And so I will find what is it individually for the cylinder, what is it individually for the hoop. Just knowing its center and its distance moved, I can get those. Then I need to know the rod also. And so I do know the rod. Add those three together and there's the answer. And so I can calculate the kinetic energy of that rotating mess. The hoop, the cylinder, and the rod. Fair enough? And so that's what we're heading to. That's what we're trying to do. What is this energy? And also, like I said, moment of inertia shows up for Newton's second law also. We haven't done that quite yet. That's coming real soon. How are we doing on time? Oh, so maybe I'll hurry up and get to it. But I do want to do the hoop and the cylinder, and then we'll move on here. So maybe the first thing to do, let's see, is I finished here. So let's go and do the hoop. What is a hoop? And again, I need to specify about its center. But now you can begin to see that usually we mean all the time about its center anyways when we're talking about it. Because if you know its center, you can apply the parallel axis theorem and figure out what it is when you're not at its center. So let's find it about its center. Again, why don't I start with this integral of r squared dm. Why don't I put a picture right above it? This would be kind of the shape of the hoop, if you will. I'll put a coordinate system, and right at the center, that'll be the axis of rotation. And this one is actually even much easier than the rod, because what do you notice about r in this problem? Yeah, And your author then says, call the total radius of the hoop, capital R, all those little masses that you're going to be adding up. In other words, if I were to take this and chop it into little pieces and go cut, 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 all those little masses you're adding up are all at the same distance away, capital R. And so I'll replace little r with capital R and then realize it's a constant, so I will pull it out in front. And then it becomes really easy. What is the integral of dm? That's just the sum of all the masses as you go around, and so you just get a capital M. Your author writes it like this. He says, here's the moment of inertia of a hoop. It is mr squared. Ta-da! Told you that was the easy one. And maybe I should have started there, but it was too simple. I wanted to do the rod there and the parallel axis theorem. But the hoop, sometimes called a ring, is pretty simple. But now, what about the disk? And I hope this kind of sets up the recipe. How am I going to get this disk now? Right, do you see that mental picture? That a cylinder is a sum of a bunch of rings. In fact, it's kind of why we have this one here, so we can kind of draw on it and say, look, here's the disk. If you think of this as the inner ring there, then add to it the next ring, and add to it the next ring, and add to it the next ring, and so eventually you get to the very last ring, which if we call that capital R, then that's going to be our moment of inertia of a disk. So, oh, and I said disk, but I guess I should also say disk, cylinder. Does it kind of look like the same thing to you? I mean, it's still a cylinder, just cylinder, for whatever reason we like to call things that are tall cylinders and things that are short or a disk, but there's the same geometric shape here. And so what is then this moment of inertia about its center for a cylinder or for a disk? All right, well, I would probably write it this way. What is I for a cylinder, or if you like, a disk? And again, I guess to be technical, I should be saying about its center. Okay, so I've got the hoop. And again, the mental picture, maybe I'll put it back here, is this, that I've got this disk of radius r, and the mental picture to have is I am going to take a little ring and another ring and another ring and another ring and another ring and another, or a hoop, a hoop, a hoop, a hoop, a hoop, and add up all these hoops or all these rings until I get my cylinder or my disk here. Okay, so I guess what I have is the sum of a bunch of hoops. So now you can see why I did the hoop first. Right? So let's see how we're doing with our calculus. This is the sum of mr squared, or maybe I'll put an mi on an ri, and I'm going to take an infinite number of hoops, right? Cut it in thinner and thinner and thinner. So the limit as what goes to 0 here? Is it r? And so I have this disk here, and maybe I'm looking at this ring out here, cutting it thinner and thinner and thinner. Is the radius of that ring going to 0? The mass is, right? Cutting them thinner and thinner and thinner. So it's the limit as the mass of goes to 0. So in other words, this becomes an integral of r squared dm. Now, I'd be careful here. This kind of looks like this integral back here. But there is something very important and different here. Because what is, say, this dm here compared to, say, this dm? What is this the mass of? A ring, right? This is the mass of the ring. What was this the mass of? Yeah, a little chunk here, right? Just a little chunk of mass. And so it looks like it's the same, but it's not the same, and I need to remember that as I go to draw my picture here. In fact, I think I'm going to need a bigger picture here. So I'm going to take it like this. There is this whole cylinder, and I am going to take and kind of draw a ring in here. And what this dm means is the mass of the whole ring. And what does the r mean? The r is the radius of the ring. You see, because I started here, I'm adding a bunch of hoops. And so that meant the mass of the ring and the radius of the ring. So keep that in mind. This is the ring. In fact, I run into a little notation problem here because I'm using a capital R here for the radius of the ring. Do all these rings have the same radius? No. So that capital R changes, doesn't it? So what do you want to call the whole radius of this cylinder? Do you want to call it capital R? I mean, that's what I did here. And I only did it because your author did it. But that leads to some confusion, because if you call this capital R here, then we probably shouldn't call this the capital R. Or if you want to keep that as capital R, then I should probably change this one. But I shouldn't have them both capital R. And I think it's probably best to change it the way your author changes it. He says, let's use capital R for the radius of the whole cylinder when we're done. So let's change it here. So what he does is he goes back and calls this a lowercase r, and he calls this a lowercase m, so that he can then say the total mass is a capital M and the total radius is a capital R. And so he's really kind of doing the same notation here. The little things add together to give you the big things. But now the little things are the hoop, which were the big things. So that's why the change from big to little, so that we can integrate them and go back to big. So just be careful you see that in the notation. Otherwise you might not kind of catch what he does, and that just can lead to some confusion there. But that's what he does. He makes that little switch there. All right. So as long as you understand that little switch, let me ask you this. What are you going to do next? You can't really do an integral with a dm, so we need to switch it to something, right? Good. Density. Heard somebody say, well, let's look at the density. What would be the density of that ring or that whole cylinder? Right. It would be a little bit of mass over a little bit of area. Which comes back here. What do I want to know? I want to know the mass of a ring. So let me put mass of ring. So this would be area of ring. And so my first step would be this. This would be an r squared, where r is the radius of the ring. And I would replace that with density times area of ring. Because that would let me do the next step. So this is r of the ring. Okay, don't forget that. This is density. Okay. What is the area of this ring? This is the kind of whole reason I tried to shade this in. How would you get the area of this thing? Okay, I heard the first part, a pi r squared. Wouldn't that be the circumference? You can imagine kind of cutting this and laying it out. I mean, wouldn't it look something like this if you kind of cut it and laid it out? And its length would be 2 pi r, right? So I would say the area of this is 2 pi r, and again, r being the radius of the ring, but not done. What else? The thickness of it, which is my dr. These are my little things. How thick is that ring? And so that little ring has a thickness of dr. Finally, I got to an integral that I am liking. Something that you are used to in your math class, your physics 150. See, this is the part that, like I said, I think is the hardest, and the part that, you know, I'm trying to train you for is, could you go from this question, what is the moment of inertia of a disk, to the conceptual picture of, oh, well, that'll just be a sum of a bunch of hoops. The hoop is this equation. I take the limit as they get smaller. That gives me an integral of a dm. The dm becomes a dA, the dA becomes a dr. Now the easy stuff begins. Okay? But it's this whole idea of doing this, what I call, again, reading the math. You're not so much doing it, you're understanding what does the calculus mean here. It's why I said before, and I haven't said it in a while, so maybe it's worth saying, if all you do in this class is treat it as a math class and this plug and chug, and say, all I got to do is memorize the formulas, and I'll just plug them in and get an answer, you'll run into a lot of troubles. There's a logic behind them. There's not a whole lot of memorization of formulas, but there's a lot of detail of what does each mean and how it is different from one problem to another. But I can't resist, so it's worth saying, because if all you do is plug and chug, you'll do okay. You'll survive and get an okay grade. You'll transfer to an okay school, have an okay career, with an okay spouse, with an okay life, and okay kids, right? No. But it's so much more than that, and this is well illustrated here. And once you get to here, now you're just at your calculus, which I say just your calculus, but you're going to find this the easy part. This part here forward is pretty easy. Watch. I mean, now let's actually finish the problem. So as I go to finish this problem, like I would do any integral, I would find out what are my constants and get them out of my way. So the 2 pi and the rho I'll pull out, and then I'll have my integral of my r squared of my ring. Oh, excuse me, r cubed. There's 3 of them. And then it's my dr. And then I can come back to my picture and ask, well, what are my limits of my integration? What am I adding up from? Yeah, 0 to big R now, if we're going to call the total radius then of this ring capital R again. So this becomes the 2 pi, this becomes the rho, this becomes the r to the, well, I'll just do a substitution at the same time. So it's capital R to the 4th over 4. And so there's my integral. Now once I've done my integral, I got that one last step. How do I get rid of density? Well, it's the same thing as before. I introduced density back here at the beginning by saying it's a little bit of mass over a little bit of area. But wouldn't that also be the same as all the mass over all the area? So what's all the area of this disk? Yeah, pi r squared. So this becomes 2 pi times an m over pi r squared. And then I've got my r to the 4th, and then I've got the 4 down there. So the pi's go away, 2 of the r's go away, the 2 upstairs cancels partially with the 4, and it looks like I'm left with a 1/2, I'm left with an m, and I'm left with an r squared. And so there is the rotational inertia of a cylinder or a disk. You know, what is it? And then for this, it's 1/2. And again, if you've got a chance to look at the table in any way, you'll see that. It's right in there. So I ask again, but unfortunately, well, I don't want to get bogged down in the problem. We'll do this when we do example problems next time. But could I now get the moment of inertia of this crazy thing? Right? I know the formula for a hoop, together with the parallel axis theorem would tell me what that is. I now know the formula for a disk, together with the parallel axis theorem would give me that piece. And then the rod, and this is about its center, so I won't need the parallel axis theorem there. Add those three together and boom, I got it. And so that's my warning for you. You've got some good ones on the homework. One of them is a tire on a car. And it says, what is the moment of inertia of this tire? And they ask you to think of a tire as having the tread part, which goes all the way around the tire, and then the sidewalls, which is really then a disc with a hole in it. And so you take one sidewall, you take another sidewall, you take the tread, you figure out the moment of inertia of each of those separately, you put it together, and now you find the moment of inertia of this tire. And so you can see where you're going with this. You're pretending you're, the mechanical engineer, you're working for GM, and you want to know, what is the moment of inertia of this tire, and we've got to make it spin with the engine and stuff, and so how difficult or how much energy is there as this tire is spinning here. Oh, another neat one is it's got these three rods. Don't really have three rods, and I don't want to take that apart because I want to use it here real quick. But it's got one rod sticking out like this, and so here's the pivot point. So when you let it go, it can fall. But then it's got a second rod that is mounted this way, and a third one that's mounted this way. So it looks like the three axes on an X, Y, Z grid. The X-axis, the Y-axis, and the Z-axis. And then it's mounted on this end and it falls. So what's the rotational inertia? I'll let you think about that. I want to take away your fun. I mean, what else would you be doing Saturday night? So that's where you'll be spending your time figuring out what is the rotational inertia of those. Well, like I said, and I spent quite a bit of time there, maybe even too much time, but just understanding that concept of the moment of inertia, together with doing some of the calculations, can get pretty tricky, if you will. Well, there is one last thing. Well, maybe it's more than one thing, but I'll start with one last thing, and then it kind of builds here. And it fits right into this category. Oop, didn't want to erase that one. But as we get to the end of the chapter here, we've covered just about everything. Let's see, we've covered the kinematics, we've covered energy. The thing that hopefully you're noticing we're missing is Newton's laws of motion here. So maybe I'll start with Newton's first law of motion. Newton's first law of motion, back in chapter 5, said an object at rest wants to stay at rest, and an object in motion wants to stay in motion. What kind of motion? Right, constant velocity, same speed, same direction. Well, the same thing works for a rotation. There's nothing I can really put in that chart, but I can say this. If I have an object at rest, it wants to, well, it's not balanced. It's at rest, it wants to stay at rest. But if I have an object that's already spinning, it wants to stay spinning. Unless acted upon by a external torque. Anybody remember that word from 102? All right, so when it comes to making things starting and stopping rotating, like now I'm slowing it down, am I applying a force or a torque? And it's really torque, right? So torques make things rotate Forces make them translate. Okay? So, you probably can guess this here, that Newton's second law then looks like this. Acceleration is equal to what? Net force divided by mass. Applying that over here, angular acceleration would be what? Maybe I'll start with the denominator. Any guesses what might go down here? Okay, there's the I, right? There's the moment of inertia we've been talking about for the last hour. Okay, so even though we saw it for the first time when we talked about energy, that would be its resistance to change its state of motion. As I tried to show earlier, something with a lot of rotational inertia would be hard to get it to spin, or once it's spinning it would be hard to get it to stop. Okay, so you kind of saw that. But the last step for this semester is what would go up here? Torque. Right. And the symbol we are going to use then for torque is the Greek letter tau. Okay, and so we're back to our Greek letters. And so notice that with the exception of I there, they're all the Greek letters, purposely, to try and make sure you keep that straight in your mind. What is the physics of rotation and what is the physics of translation? Okay, and so there's our torque. Now, I showed you this in 102, but it's worth repeating. Is torque and force the same thing? No, it would be like me asking you, is mass and moments of inertia the same thing? No, what was the difference? Yeah, moment of inertia was a little more complicated. It had an R in it, an R squared to be particular, right? The same thing can be said here with torque. You might remember this one from 102. This door is probably the easiest illustration. If I take the door and I walk out the door, don't I have to pivot the door? So to open this door, do I need a force to open it or a torque to open it? Right, correct semantics here, and it's not just semantics. There is a difference between torque and force. What I want to illustrate, correct semantics, is it's a torque. I got to apply a torque to this door. And what you've probably have maybe seen is when somebody walks up to a door, if they know which way it opens, and you do, here's the hinge over here, where do you push on the door? Don't you push here? Because you have to apply a torque. And what I want you to see here is the torque is a combination of how much force from my hand, but also how far away I am. Because if you've ever tried to open a door pushing here, you still got to apply the same torque. But because you're what we'll call a lever arm, your distance is less. For you to open the door, well, you can get enough torque. But how do you get all that torque? It's more by a lot of force because you don't have much distance. And so many of you will remember that that's a combination of a force and a distance. I'll do you one better, because that's what we said in 102. It also has to do with the angle you push out. So watch this. Let's say that I have some kind of object that I want to twist. I'll say it again. I want to twist it. Here's a bolt. I want to either tighten it or loosen it. Do I want a force or do I want a torque? Yeah, I want a torque. That's how you can, I guess, easily tell if somebody has had an education or not. What is the right terminology do they use here? I mean, do they call omega omega or W? Do they call torques forces? You know, what is this whole idea here? But this is a torque. I want to apply a torque to it. And many of you have probably used a wrench and noticed a difference between holding it here and pushing on it, I'll call this F1, or holding it here and pushing on it, F2. To tighten that bolt, or maybe I should have done it the other way, so I loosen the bolt, but to tighten it or to loosen it, I want a certain amount of torque. And like this door, if I apply the force out here and it pivots around the center, I can get the same amount of torque with a lesser force here than there. But watch this. What if I grab it out here, but I push it this way? Does that give me much torque? In fact, I'll do you one better. What if I grab it right here and I push it this way? Yeah, I don't get any torque there. So, one thing we didn't quite do in 102. In 102, we just said it was force times lever arm, force times distance. Because we didn't get bothered into the trigonometry, the sine and the cosine of the angle. But that is an important piece here. I would say this is true. If I were to take this force, let me just look at force number 3 here, and say, here is force number 3 pushing like that. I could take force number 3 and think of it as how much is perpendicular to the radius going in, and how much is parallel going in. And as many of you saw there already, the force that goes straight towards the bolt, does that give you any torque? Does that make the bolt turn in any way? No. So that part is irrelevant. The part that you want is the part that is perpendicular. So it may not be the total force. Now, the smart move here would be make sure you grab the wrench and you push perpendicular. So all the force is being used, not just a component of the force. But so that we can write it out, we're going to write it this way. What is torque? Well, it is a combination of F sine theta. Now let me define theta here. What is theta? Well, in this picture, this is my theta. I guess it would be this picture here. But I'm going to define theta as the angle between my F and my R. And so there's the R that most of you are familiar with from the lever arm. And so the R part of it is coming out here. And many of you probably remember an experiment that we did, something like this, where I said, okay, let's see how I can change the acceleration of this platform. And this illustrates all the pieces of Newton's second law here in rotation. Because if you come over here, you already saw the first, what I'll call, 2 pieces. You saw me change the acceleration by changing the moment of inertia. You saw this. You saw me first just let it go and say, wow, that unwinds pretty fast. But then I added more mass to it. And I said, well, that's going to give it more rotational inertia just because it has more mass. So when I let it go again, it was a little more sluggish. And then you even saw the second one where I said, okay, let's then put the mass at a distance further out. And I was trying to illustrate that that would give it a larger moment of inertia. And see how much slower this is. I'm going to do one more thing. What if I leave the weights here and I take this string and I wind it up on a smaller pulley? What's that going to change? Yeah, doesn't it change the R factor in the torque? And if I let it go now, it should be really sluggish. Because I have a big moment of inertia with all that weight spread out. And then I have a small torque because I have a small lever arm there. And so that's this piece of the puzzle. So what you will see, looks like we're going to be out of time here for today, is the final piece of this is RF sine theta is going to be our equation here for torque. And so the torque is a combination of not just force, but it's force, distance, and angle. And so we got to look at how it is being unwound. And obviously, the best angle to have is 90 degrees. Sine of 90 degrees is 1. All right, well, work on these. I'll do examples for you on Monday. It's taken me a while to get through these 2 big chapters. I told you they were kind of long. But the flip side of this is you got 2 short ones coming up. So then we can do it. Yeah, 11 and 12 are pretty short. I guess the negative thing, though, is when we do these next 2 ones, now we're ready for a test again. Could it be that quick? Where'd all the time go?